Hi everyone, I'm Diyang. I'm glad to present our work, PRISM, a primitive-centric framework for skeleton action representation. This is joint work with Yaohui Wang, Shuai Shao, François Brémond, and Jiangtao Wang. Skeleton-based action understanding is robust to background, appearance, and lighting changes, and is also privacy-friendly. We focus on three related tasks: action classification, frame-wise action detection, and motion generation or transfer. Existing methods usually train separate models for generation, classification, and detection. This creates fragmented pipelines and prevents knowledge sharing. In addition, common skeleton embeddings often entangle motion, viewpoints, and body identity. This limits transferability. Our proposed PRISM learns a shared primitive coefficient space. Each action sequence is represented as a trajectory in this space, where each coefficient describes the contribution of a motion primitive. This makes the representation structured, compositional, and transferable. PRISM has two main stages. In the first stage, the encoder maps a skeleton sequence into primitive coefficients at each frame. These coefficients are combined with a learned primitive dictionary to form a latent representation, which is then decoded to reconstruct the skeleton motion. To learn view invariant motion, PRISM separates the representation into motion coefficients and static coefficients. Motion coefficients capture dynamic movement, while static coefficients capture viewpoint, body shape, and orientation. Static swapping encourages the model to disentangle these factors. The second stage, primitive coefficients are structured, but they may miss local context. Therefore, PRISM uses a context-aware skeleton encoder to extract spatial temporal features. The temporal feature fusion combines these context features with primitive coefficients for action classification and frame-wise detection. The PRISM learns the primitive space with reconstruction, cross-view swapping, physics-inspired losses, orthogonality, and sparsity. Then, the learned primitive encoder is transferred to downstream perception tasks using standard supervised losses. We evaluate PRISM on several datasets for multiple tasks. For action classification, PRISM achieves state-of-the-art accuracy on positics. It also performs strongly on Toyota Smart Home Trimmed (TST) under both cross-subject and cross-view settings. This shows better generalization under long-tail distributions and viewpoint changes. For action detection, PRISM also achieves state-of-the-art on Toyota Smart Home Untrimmed TSU and Charade. This shows that primitive coefficients are useful not only for classification but also for detecting overlapping and compositional actions. PRISM also supports motion transfer and action composition in the generation task. By preserving motion coefficients and replacing static coefficients, it can generate motion under new views or identities. By combining primitive coefficients, it can synthesize compositional motions. In summary, PRISM learns a shared skeleton motion primitive space for generation and transfers it to perception tasks. The learned representation is structured, view invariant, and compositional. Experimental results show consistent improvements across classification, detection, and generation tasks. Thank you for your attention.